Good afternoon and welcome to NASA Glenn Research Center's Plumbrook Station in Sandusky, Ohio. I'm Nikki Welch and I'm at our Space Environments Complex. Now this complex houses the world's largest and most powerful space environment simulation facilities. And it's where we subject spacecraft to the rigorous conditions of launch and the vacuum conditions and extreme temperatures of space. Today, we're going inside a reverberant acoustic test facility. Now, this place takes noise and vibration to a new level. It's the world's most powerful acoustic test chamber, and we're going in for a closer look as engineers prepare to test a full-scale test version of the Orion spacecraft's crew module right behind us. So we're going to go in and take a look at that. As always, we have NASA experts ready to answer your questions, so go ahead and start sending those in the comments section, and we will answer them for you throughout today's show. So to get us started with our look around this facility and tell us more about the tests in Orion, I'd like to introduce the test project manager, Miss Nicole Smith. Hi, Nicole. So to get us started, tell us more about the facility, the Reverberant Acoustic Test Facility. What does it do and how does it work?
So welcome to the Space Environments Complex, which is the world's largest space simulation facility. Specifically today, we're going to be talking a little bit about the world's most powerful acoustic chamber of its size, which is right behind us, also known as the RADIF or Reverberant Acoustic Test Facility. There are 36 horns that we use. You can see them all on the one wall to generate sound to be able to perform dynamic vibration testing on a spacecraft, just like the Ascent Abort-2 crew module that you see right behind me. We can test all the way up to 163 decibels in this chamber, which, just for a little perspective, if you stood behind a jet engine while it was running, that's about 145 decibels. So this is actually 10 times the amount of sound that we can produce here.
Okay, so we get this question a lot. Why do we need to perform acoustic tests on spacecraft or spaceflight hardware?
That's a great question, yeah. So what we're simulating here in the acoustic test facility is the very dynamic vibrations that a spacecraft will see during launch and ascent. So as the spacecraft accelerates up through the atmosphere, you have all these aerodynamic forces that are beating on it, and it gets very vibrational. And so we want to make sure that this spacecraft can survive those loads.
So obviously it'd be way too loud for us to be anywhere near here when it's on. You talked about 163 decibels. So how do you get data? Where do you observe the tests?
That's a great question. So of course we have to close this facility off because we try to reflect as much of the sound as possible. We can't even stand here where we're standing while this chamber is running because it's 140 decibels, so it's way too loud for us to even be here. But if you turn around and look, you can see some cables that are running in there. Those all go to our data systems. So we have microphones that we use to control the decibel level of the chamber, and then the test customers will read all of their instrumentation, take all the data, and then after the test they'll be able to take a look at it and make sure that everything went as planned. Our control room is several hundred feet outside of this facility, and yeah, we can definitely hear and feel this in there, and I can definitely hear and feel this thing in my office even, so it really rocks and rolls.
Okay, so before we move on to talk about the specifics of the test that you're getting ready to prepare here, I want to talk a little bit more about the Orion spacecraft. For some of our viewers who may not be familiar with the program, can you just tell us an overview of the spacecraft and its mission?
Absolutely, yeah. So the Orion is the next crew vehicle to go beyond Earth orbit. So our missions are to the moon and then eventually to Mars. There are three main parts of the spacecraft. So there's the crew module, as you see here, which is where the astronauts will be the crew. There's a service module, which provides services to keep the crew alive and to drive the spacecraft. So like power systems, thermal control systems, and the main engine. And then there's the launch abort system, which is to get the crew module away from the rocket in case something bad happens during launch and ascent.
So speaking of that, let's talk more about what's installed here. This is a test version, but can you tell us more about it and the test that you're preparing to conduct?
Yeah, absolutely. So this is the crew module for the Ascent, Abort-2 or AA2 flight test, which is going to happen down at the Cape next April. This crew module structurally is very similar to the actual crew module that people will eventually fly in, but it has very test-specific hardware in it, like avionics and power systems, and the data systems are all specific to this test. So we're going to run it through the paces here, get it up to about 155 decibels, so the engineers and designers can take all that data and check it against their engineering models and make sure that everything matches up and that they'll have a successful flight test in a few months.
Okay. And speaking of the flight test and launch abort system, we do have an image of the Orion spacecraft with the launch abort system here. So can you use this to kind of show and tell a little bit more about the launch abort system?
Okay, well, just to start out, so here's our crew module that was behind us in the chamber, so we're testing that, and then this is a fully functional launch abort system, or LAS. So there are three main types of engines on the launch abort system. So the abort motor, the jettison motor, and the attitude control motor. So the abort motor is the one that fires in case something happens with the rocket, and it pulls the crew module, and the whole thing comes away from the rocket at a really fast speed. The jettison motor, let me go back. The attitude control motor is the one that repositions the entire capsule to the right position for it to be able to eventually land. And then the jettison motor gets rid of this whole tower so the crew module can start falling towards the ocean and the parachutes can come out and they can land gently and safely in the ocean. Now, in the case of this specific test, we aren't going to be using the parachutes because we don't need to. They've been tested a whole bunch of times, but we're going to be taking data as it goes down to the ocean.
So in an emergency situation, how fast and how far could the launch abort system carry the astronauts away from the launch vehicle?
Sure, that's a great question. So this launch abort system can separate the crew module from the launch vehicle within milliseconds, and I think the speed is something like going a couple miles away within 15 seconds, so it's super fast.
So what are the next steps after you complete the test here in the Reverberant Acoustic Test Facility? What are the next steps for this test article?
Yeah, so we'll get it all packaged up and put on a truck back to Houston to the Johnson Space Center. The crew module will be mated with a separation ring, and then it'll be sent over to Kennedy Space Center, where it'll be mated with its launch abort system and the booster rocket that this test is going to ride on, and then they'll launch from the Cape in April of 2019.
Okay, so that's a really exciting time, I'm sure, for you and everybody else involved. Looking forward past April 2019, what other tests will you be performing here in the Space Environments Complex related to Orion?
Yeah, that's a great question, too. So hot on the heels of this, we'll be getting ready for Exploration Mission 1, or EM1, which is the first full-up spacecraft that will fly to the moon. It'll fly and be out on orbit for about 25 days, close to a month. But first it has to come here, and we have to put it through the paces in our thermal vacuum chamber, and also through the paces with electromagnetic interference testing. So it'll be here for about 4 months. The thermal vacuum testing is about 65 days long, and we'll make it really, really cold, minus 250 degrees Fahrenheit, and really, really hot, 300 degrees Fahrenheit. So we'll simulate the cold and the heat of space, and we'll pump it down the vacuum, so there'll be no air at all in there for quite a while. It's going to be a really exciting test. After that, too, we also have a fairing separation test. So the fairings are these covers that go over the service module, and they fall away, so they separate as it's going into orbit. It's very important that they separate properly, because if they don't, your mission is pretty much done. So we'll test that in our thermal vacuum chamber. And actually, the crew module from EM1, when it comes back, will get all cleaned up and sent back to us, and we'll put it in our acoustic chamber again and run abort level testing on it again. So we're pretty excited about all that testing over the next few years.
Yeah, that will be an exciting time. So we're going to go to Facebook and see if we have any questions from Facebook. So the question is, what material is the spacecraft made of?
This spacecraft is made out of aluminum, but a lot of other parts of our spacecraft are also made out of composites.
So the question is, does the abort system stay on after the spacecraft has reached orbit?
Yeah, that's a great question. So I didn't point out that in a nominal test flight, the launch abort system jettison motor would actually fire to get off right before it goes into orbit. So that's a great question. Thanks.
So the question is, does all of the sound that you expose the spacecraft to come from the wall of where the horns are?
Yes, actually it does. So right behind us, you kind of can't see it maybe, but there's a huge door that rolls shut and another one here that folds. So this is a big reverberant chamber. So we only have to have horns on one of the walls, but the sound waves bounce all over the place. And honestly, based on how loud we want this sound to be, we can tune how many of those horns on that wall that we have on at the same time too.
Okay, I had a question as we were talking. So when you run the test, how long do you have to run them to sort of get the data that you need to? So once you initiate that sound and that vibration that goes on, how long do those tests run?
That's a good question. So this test will run each one of them for about 3 minutes, but we can run this chamber up to about 10 minutes in length.
Okay, so they're pretty short.
Yeah.
Okay. And the other question I had was when you talked about all of the work with partners and other NASA centers to make this come together, can you talk a bit about how you coordinate?
Absolutely. So, yeah, we have a big integrated program that's all across the United States and also with our European partners who help provide part of the service module. So in the case of this spacecraft, the structures part was built at Langley out in Virginia. We talked about it being sent down to Houston where a lot of the avionics boxes and a lot of other hardware were installed. Now it's sent up here to Ohio to NASA Glenn for us to test it. We'll send it back to Johnson Space Center for the last little bit of work, and then it goes to Kennedy, and the last, which is also produced by Lockheed Martin, will be mated to it for the launch. So we work with a lot of different suppliers, a lot of different vendors all across the United States, and when Exploration Mission 1 is here, the crew module and the service module will be here, and the service module is being provided by the European Space Agency. So it's, we're across a lot of different time zones, a lot of different cultures. It's pretty exciting, and it takes a lot of integration for us to pull it all together.
Well, do we have any more questions from Facebook? Okay. Lastly, one thing I want to ask, because a lot of times we have questions from students and young people who are interested in engineering. If you could just talk about kind of your path and how someone, if they're interested in doing what you do, how would they go about that?
Sure. All right. When I was in high school, I found out that I was really good at math, although a lot of times I was very artistic, so I took ballet and I took piano and stuff like that. But I loved math, and I loved that there was a single right answer for things, and being able to find the answer to this was very challenging, and I enjoyed it. So when I started college, I was a mathematics and statistics major, and then I added the aeronautics major because they had the best toys. So I loved the rockets that we got to play with. I loved dealing with airfoils and wind tunnels, and then I went to graduate school to be an aerospace engineer. So that's how I started out. So I would recommend from anyone, one of the most important things you can do when you're in junior high or high school is really get the math classes. And you know what else? Don't feel bad if you don't do well on a test, because I have plenty of tests that I got C's on, and then I just worked all the harder and made it happen. So just have creativity, have innovation, work really hard, try to get your math classes in, and if you can do some fun things on the side like robotics or stuff like that to get experience, that's a great way to do it too.
Thank you so much, Nicole, and I want to thank you for the discussion and letting us know about your story, and thank you for joining us today. We have actually got to get out of the way because engineers need to get back to work to continue preparing this test and make sure it stays on schedule. But one thing you can do is continue to stay online. We're going to continue to answer questions as they come in, so we'll hang out a bit longer there. And if you're interested in exploring more of the Space Environments Complex, this facility and other facilities, the vacuum chamber that Nicole referenced, we have an online 360-degree virtual tour that you can check out. It has videos, images, and lots more information about the work that we do here and other spacecraft that have been tested in this facility. And the link to that virtual tour is included in this post. So once again, I want to thank you for joining us, and we'll see you next time.